All right, let's talk about a powerhouse algorithm, one that can take your code from slow and clunky to fast and super elegant. This is an absolute must-know for any coding interview. So let's just dive right in.
Okay, so let's put you in the hot seat. You're in an interview, and they hit you with this question. You've got a sorted array, and you need to check if any two numbers inside it add up to a specific target. Now, your brain probably jumps to the most obvious solution first, right?
And that's usually the brute force trap. You take the first number, check it against every other number. And then you grab the second number, check it against all the others. You can see where this is going. It's a loop inside of another loop. I mean, sure, it gets the job done, but at what cost?
Well, that cost is time. Big time. This whole nested loop thing has a time complexity of O of n squared, which we call quadratic time. In the world of algorithms, that bright red number is a huge warning sign. If that array is big, this approach is just way too slow, and any interviewer is definitely going to push you for a better solution.
But here's the good news. There is a much better way. And this is your moment to really shine in that interview, to show that you think about efficiency. So let's reveal the elegant solution, the two-pointers technique.
So what is it really? Well, the two-pointers technique is just a brilliant optimization strategy. Instead of mindlessly checking every single combination, we use two indexes, we call them pointers, and we move them through the array in this coordinated, intelligent way. The entire goal here is to slash that time complexity, usually taking it from that ugly O(n) squared down to a beautiful, linear O(n).
And you can really see the difference here. Brute force is like trying to find a needle in a haystack by picking up every single piece of straw, one by one. Two pointers, on the other hand, is like using a powerful magnet that pulls you right toward the needle. You're just intelligently zeroing in on the solution. It's all about working smarter, not harder.
So when should this light bulb go off in your head? Well, here are the signals. If you see a problem with a sorted array or a sorted string, your first thought should be two pointers. If they're asking you to find a pair or a specific kind of subarray, think two pointers. And honestly, if your first instinct is to write a nested loop, just pause for a second and ask yourself, wait, can I use two pointers?
Now, to really master this, we're going to break it down into a toolkit with 3 core patterns. Once you get these down, you'll be able to solve a massive range of problems.
First up is the opposite direction pattern. This is the classic. It's exactly what it sounds like. You put one pointer at the very beginning of the array and the other one at the very end. Then you just move them toward each other until they meet in the middle or cross paths.
This pattern is your go-to for that original problem we started with, finding a pair that adds up to a target in a sorted array. It's also perfect for things like reversing an array right where it is without using extra memory, or for solving another super famous interview problem called container with most water.
Now here's the magic of why this works so well on a sorted array. You start at the two extremes, right? The smallest and the largest numbers. If their sum is too small, what can you do? Well, the only way to make the sum bigger is to move the left pointer to the right, to a larger number. And if the sum is too big, you have to move the right pointer left, to a smaller number. See? Every single move eliminates a whole bunch of possibilities and gets you closer to the answer. It's a greedy approach. Every move is the absolute best decision you can make at that moment.
Okay, on to our second pattern. What if, instead of moving towards each other, our pointers move in the same direction? This is what we call the fast and slow pointer approach. Both pointers start near the beginning, but they move at different speeds or based on different rules.
This one is the key to solving problems like removing duplicates from an assorted array without using any extra memory. It's also great for partitioning arrays, and here's a famous one for detecting if a linked list has a cycle. You have one pointer move one step at a time, the other moves 2 steps. If they ever land on the same spot, boom, you've found a loop.
So let's walk through that remove duplicates idea. Think of the slow pointer as the gatekeeper. It marks the end of the clean, unique part of the array. The fast pointer is the scout. It goes exploring ahead. As soon as the fast pointer finds a number we haven't seen before, it basically shouts back to the slow pointer, hey, got a new unique one for you. We copy it over, and the gatekeeper moves up one spot. It's just a really elegant, in-place solution.
All right, our third pattern is a really dynamic and powerful one called the sliding window. Here, the two pointers don't just point to individual elements, they define the boundaries of a window over the data. And this window can expand and shrink as it slides along the array, looking for some kind of optimal section.
You'll want to use this pattern whenever a problem asks for something like the longest subarray or the shortest substring that meets a certain condition. Things like finding the maximum sum of any subarray of a specific size, or the smallest window that contains a certain set of characters.
The rhythm of the sliding window is everything. First, you expand the window from the right, adding elements one by one until your condition is met. Then, and only then, you start shrinking the window from the left, trying to find the tightest, most optimal window that still works. You expand, then you contract. It's this greedy little dance that gets you to the best possible answer super efficiently.
So you know the patterns. Awesome. But in an interview, just solving the problem is only half the battle. You have to communicate how you solved it and why your solution is good. This is how you really stand out.
I want you to memorize this. Seriously, this is your power phrase. It's short, it's packed with killer keywords like greedy decisions, linear time, and constant space, and it tells the interviewer that you don't just know the answer, you understand why it's the right answer. It shows you've got a deep grasp of the core principles.
And while you're nailing that explanation, make sure you sidestep these common pitfalls. The biggest one, by far, is trying to use this on unsorted data. That opposite direction pattern completely falls apart if the array isn't sorted, because your greedy decisions won't work anymore. You always need to be ready to explain why your pointer movements are logically sound. So, why does all this matter beyond just passing an interview? Because this isn't just some clever trick. It's a fundamental way of thinking about efficiency, about memory, and about how to use the structure of your data to your advantage.
And for those of you in or aiming for machine learning engineering, this is incredibly relevant. These exact patterns pop up all the time in data preprocessing, in creating streaming windows for models, segmenting time series data, even in doing feature engineering without blowing up your computer's memory. It shows an awareness of efficiency that's absolutely critical when you're working with massive data sets.
If you take away just one single thing today, let it be this. 2 pointers is the art of control traversal. You are leveraging the structure in your data, like the fact that it's sorted, to make smart, efficient moves. That gets you fewer comparisons, linear time, and constant space. That is the trifecta of a beautiful, optimal algorithm. And that pretty much brings us to the end. With these 3 patterns in your toolkit, just think about what else you can optimize now. Problems that might have seemed tough before, like squaring a sorted array or finding triplets that sum to 0, they suddenly become way more approachable. So, what are you going to solve next?